Hello, my name is Zheyun Wang. Today we present our CVPR paper, a unified model for compressing the MRI across undersampling patterns. Our task is MRI reconstruction. The forward model transforms this knee image to the machine measurement via a Fourier transform with additional noise. The machine measurements are then downsampled to reduce imaging time, which also makes the inverse problem going from measurement to knee relatively ill-posed. For the inverse problem, we thus use the parameterized deep learning model f-theta to learn the mapping between the machine measurement and the underlying image for the MRI reconstruction. Recently, neural networks have shown amazing results for MRI reconstruction, which goes from this downsampled MRI measurement to the image. It has improved the diagnostic performance for different organs and shown robust performance on unseen protocols and scanners. However, undersampling patterns change in real clinics, and specific network is needed for specific measurement pattern. We propose neural operator, an extension to neural networks, which has resolution-agnostic architectures and work on all different downsampling patterns and rates. What is neural operator? It is a deep learning architecture that can learn mapping between function space at infinite resolution. It also works for diffusion and iterative methods, although this paper focuses only on the end-to-end mapping. The neural operator has following advantage. It can approximate the physics of this inverse Fourier transform, the imaging process, which is resolution agnostic. Multi-resolution training can also be enabled with this neural operator model to enable learning from low-res to high-res across different samples during training. The resolution-agnostic architecture will also allow inference on any resolution, greatly increase the flexibility for the inference method. Let's look at a specific example. For an input knee image, the state-of-art convolutional neural networks learn different convolutional kernel or weights to transfer the input to the output feature map with a sliding window at different location. We can visualize the kernel on the top. This works great for single resolution. However, when the image resolution increases, for example, from 100 to 200, the kernel size stays the same, and the receptive field gets relatively smaller. And when the resolution of the image decreases, the receptive field gets relatively larger. The three receptive fields operates at different scale for different resolutions. This can cause problems for reconstruction. The proposed convolutional neural operator, on the other hand, learns convolutional kernel with infinite resolution. Based on the input feature size, it can discretize to different resolution. For example, 12 by 12 for 200 by 200 input, 6 by 6 for 100 by 100 input. This convolutional neural operator operates in the continuous function space with infinite resolution, and then the kernel can seamlessly rescale to different resolution based on the input resolution for consistent receptive field and avoids artifacts for reconstruction. But how do we learn and optimize an infinite dimensional kernel in common deep learning framework which uses discrete optimization? The idea comes from basis decomposition. The kernel is parameterized as a weighted sum of predefined basis function in the infinite dimensional space. We visualize the first basis functions, which are continuous. Instead of learning these continuous functions, we can then learn the weights of these discrete parameters, and we thus call this convolution discrete continuous convolution. Other layers are the same as the CNNs, such as the nonlinear layers ReLU. In practice, our kernel is defined in continuous space, or the function space. It allows training at any discretization, That improves the data efficiency during training. The network also allows inference at any resolution with consistent performance. As a reminder, kernel and basis are rescaled to corresponding input resolutions. The proposed convolutional neural operator is an efficient local integral operator, which is optimized for GPU computing. It is imposed in both image and frequency space, which is natural as MRI machine measurements are in frequency space. Due to the duality of the two spaces, we learn both global and local features. We also adopt the U-shaped architecture for the convolutional neural operator to capture multi-scale features by resizing input images and allow mid-size receptive. The proposed neural operator is optimized for image. Compared to an existing popular neural operator FNO, which is well developed for PDE learning. Our method considers the identity of images, which is in the full frequency space, whereas PDE data are smooth functions and high frequency data is usually irrelevant or noisy. Due to this different data prior, we consider the full frequency data, whereas FNO discards high frequency data. This is a fundamental issue and avoiding us to directly applying FNO to images. Additionally, we have a larger receptive field, K by K, instead of using a local one-by-one kernel in the FNO. For MRI, downsampling patterns usually happen in the frequency space, and the K by K integration can learn to transfer knowledge between different frequency downsampling patterns. For the results, we first consider making the inverse problem harder and more ill-posed by increasing the downsampling rate. The method is now the state-of-art for MRI under different downsampling patterns. We outperform state-of-art end-to-end method diffusion and traditional solvers. We also consider zero-shot super resolution. The goal is to test the extreme case. What if we train on one resolution and test another on same resolution? The training data is 300 by 300 for knee reconstruction, where the test data is 600 by 600, and we observe a reconstruction with less artifacts. We also consider extended field of view for MR reconstruction, which is actually frequency space super resolution. Specifically, the training data is the local 150 by 50 center of this image, and the test data is on the whole image. And we also observed an improved visualization and numerical performance with neural operator. Thank you, and please come to our poster.